Good morning to all of you. So maybe for 2-3 minutes, please go through whatever we did so far, and if you have any questions, you can ask. And please submit your assignment today, hand over to Mr. Babu. Those who have not already submitted, please submit your assignments today. So are there any questions? There are no questions, so are there any questions? So if no, then let me start. So see, in the last class, I'll just briefly summarize. So we started with Euler-Bernoulli beam element. So of course there are assumptions associated with Euler-Bernoulli beam element. So what we said is beam is thin, and from the beam we separated out one element and drew its free body diagram with a local coordinate system kept having origin at left end. So we call this as local node 1. This is local node 2 of the element, and the degrees of freedom we said based on the weak form of the governing equation that we need to have transverse displacement variable as well as its derivative. So this is your theta 1, which is dv by dx. It's not an independent, but it's actually derivative of v with respect to x. And then we had v2 and theta 2. So these were the degrees of freedom, and we also had drawn the free body diagram of the element. So the free body diagram we said no that the forces are, one is the distributed force if it is there, so which is force per unit length, say Q, that was one. Then we said that no, there are bending moments and shear force on the left and right. So right side we said that shear force is, let us say, S2, bending moment is M2. I had no just change the notation to keep them simple. So S2 and this was the bending moment M2. So this was a free body diagram. So this is the element we are considering. So minimum what we have is these two nodes, and at each node there are 2 degrees of freedom which are primary variables, that is V1 and theta1 at both the ends. So we will have to have finally know the 4-term approximate solution. So that is what we had said. And so finally what I said was that looking at these primary variables has degrees of freedom at end nodes, V as a function of this local x coordinate has to be assumed at a0 plus a1x plus a2x square plus a3x cube. So this is the minimum polynomial we need to assume, and in this case actually it is dictated by inter-element continuity requirement, that is continuity of these primary variables V as well as derivative across the element. So we need to have that is essentially due to that we have these 4 elemental degrees of freedom, so we should have these 4 unknown constants. And then what we did by expressing these a0, a1, a2 and a3 in terms of values of these variables v1, theta1, v2 and theta2, we finally rewrote this as v of x is equal to h, which is the interpolation matrix, Hermite interpolation matrix, into dE, where dE is the vector of elemental degrees of freedom. So we said that where this h is 4 Hermite interpolation functions h1, h2, h3, and we also had talked about the properties of these, and vector of elemental degrees of freedom dE was v1, theta1, v2 and theta2. So this is what in brief we had done in the last class. Of course we defined what are the expressions for h1, h2, h3 and how we get them, the derivation, all the steps we had done. So now the next step is actually to substitute this approximate solution in the integral functional. So if you look at the integral functional, we need to slightly rewrite that. So now if you consider integral functional, we had derived it. So the integral functional I is half of integration 0 to small l, and then ei, and then we had d2v by dx square. So again, since dv by dx is going to be in terms of the product of matrices and vectors, so you write again in the form of transpose. So d2v by dx square transpose, it was essentially scalar, so you can always write d2v by dx square whole square as d2v by dx transpose into d2v by dx square dx. So this is the first term, which is strain energy part of the integral functional. Only thing is this term we have written as d2v by dx square transpose, one and the same thing basically, d2v by dx square. Then we had second term, which is integral 0 to L potential of external distributed force. So that was v q dx, we can write that as v transpose q dx. Again it it's basically the same thing because v is scalar here, so one can write it like this. And then the last term was potential of these forces acting at the two boundaries of the elements. They are kind of internal forces here, right and left hand. So you have this was can be written as in terms of a vector of elemental degrees of freedom v1 theta1, v2 theta2 transpose into, then you have this side minus s1 and minus m1. If you can look at that expression, minus m1, and then you have s2 and m2. So this is your integral functional. And now we substitute the approximate solution which we have assumed here by looking at the differentiability requirement within the element and the continuity requirement, for finally writing it in this form. So if you substitute this, you and take the variation of phi equal to 0, that gives you the element level governing equation. So before we do that, we also need the second derivative of v. So you would see that d2v by dx square would actually be directly the derivatives of the shape function. So d2 h1 by dx square d2 h2, because v is h1 h2 h3 h4, and these h1 h2 h3 are the ones which are functions of capital X. So differentiation of v means differentiation of these shape functions. So this is dx square d2 h3 by dx square and d2 h4 by dx square into, of course, this d, which is v1 theta 1, v2 and theta 2. So this will give you the derivatives. Let us call this as also b, as far as the notation is concerned, b into de, where b is basically this. And if you look at the shape functions, they are cubic in capital X. So when you differentiate them twice, so basically b will involve terms linear in X, capital X. So this is, I am still calling this as b, kind of strain displacement matrix, because if you remember, as far as the strain is concerned, if you look at epsilon xx, we had written as minus y times d2v by dx square. So essentially, are in the local coordinate system, epsilon capital xx as minus y d2v by d capital X square. So you would see that still the strain is governed by now the second derivative of v. Of course, you will need to multiply it by minus y to get the strain at any y. But the main term here is this, so we still call this a matrix of second derivatives of the shape functions as B matrix. And then you substitute this in the integral functional. So if you look at now, substituting the approximation of V in I, we will get I is equal to, the first term is half integral 0 to L, and now see first is d2v by dx square, which is now d2v by dx is this. So it's transpose, that is the first term if you look at here. So it's d2v by dx square transpose. So when you do the transpose, you get here d transpose, then b transpose. Then second term is d2v by dx square, which is directly b into de. And then of course that integration with respect to x, so that is dx. This is the first term. The second term is, ei has to be there, so let me put here ei, thanks for reminding me. So this is then minus integral 0 to L, and the second term is this b transpose into q. So since b is h into de, its transpose would become d transpose into h transpose into q dx. That's the second term. Of course, the third term remains as it is, which let me write as de transpose. So that is, so that when you multiply, you get the potential of these internal forces which are acting at two boundaries of the element. That is this last term. So d, that can be written as d transpose and into those forces which are minus s1, minus m1, s2 and m2. So this is what you get as your actually I. And again you can slightly rewrite this. See, if you see here, de is only the values of v and dv by dx at two ends. So they are independent of your capital X coordinate, that element local coordinate. So you can take this d transpose left side and d on the right side out of the integration sign. So you can actually write then that half of essentially de transpose integration 0 to L. E I am keeping it inside because it could be function of x. Of course, as special cases, this might be constant. So then you have ei b transpose into b dx. So this is what you get at the center, and this is your de. That is, this d is taken out of the integration. Similarly here, so minus integration 0 to L. This side I'll put d transpose out of the integration, and then you have this h transpose into q dx, and then minus, of course, you have again the last term which is d transpose and into these forces minus s1, minus m1, s2 and m2. So this is now actually this is the matrix which you call as your stiffness matrix. So we rewrite this as I half of de transpose into KE, that is element level stiffness matrix, into DE. So this matrix I am denoting, whatever you have got here, you call this as element level stiffness matrix KE. Let me call this integral as F external for the element. So then this term can be written as minus DE transpose into F external for the element, that is load vector due to external distributed force, and then minus you have this DE transpose, and let us call this quantity as we did earlier, F internal for the element. So I can write this as F internal for the element. So this is what you get as your I, and where K, already I have said here that this is your K, this is F external, this is F internal. And then now the solution of original differential equation is equivalent to delta I equal to 0. So for equilibrium of the element, because we are considering equilibrium problem, so for equilibrium of the element, because the entire beam would be in equilibrium, so therefore each and every part and also this element must be in equilibrium. So for equilibrium of the element, we need to have delta of I equal to 0. And that again if you look at this is a product of two terms, but since K is symmetric, as you see it's B transpose B, so going to give you a symmetric matrix. So when you take delta of D transpose K D plus D transpose K delta of D, one term can be written like the other. So finally you get the expression for delta I is equal to basically you can write that half goes, so what you will have is delta of this variational operator D transpose into KE. These steps I had done when I derived actually the rod element, the truss element, and so you get the variation of this term is delta of D transpose KED, which is coming from sum of two terms, since finally the product is scalar, so we can finally write it the two terms, one like the other, and then write it like in this fashion. Then the second term is also similarly delta of DE transpose F external, this is known, so there is no variation in that. And here also we are taking this actually known in terms with respect to variation, so we only then have to take the variation of the first term. So delta of DE transpose, so we are treating basically this as an exact solution, so that is what we use in our boundary conditions. So this is F internal for the element, and this must be equal to 0. So yes, so then see now in all these three terms, delta D transpose, delta D transpose, delta D transpose here is common. So you take that out common, and since delta D is arbitrary, the variation in your vector of elemental degrees of freedom is arbitrary. That means you can choose any set of values, of course the values, not a function. So maybe any one is non-zero, or two are non-zero, three are non-zero, fourth is 0. So any combination, this equation should give you 0, and that is only possible if KE DE actually minus F external minus F internal is equal to a null vector. So if you take them to the right hand side, you can write this as F external for the element plus F internal for the element. So in between steps we had done earlier. So you call this as element level governing equation. So again the form of the equation is same, but only difference is that the sizes of the matrices, if you see, so here if you look at the way we had that we have defined Q, this K is integral 0 to L EI B transpose B dx. So see B is a 1 by 4 matrix here, and transpose would become 4 by 1. So as you see now KE is going to be a 4 by 4 matrix. So for this beam you have the stiffness matrix, which is a 4 by 4 matrix. So this is a 4 by 4 matrix. If you similarly look at the external load vector, which is a 4 by 1 vector, that is integral 0 to L H transpose into Q dx, and H is 1 by 4, so transpose is 4 by 1. So this is basically a 4 by 1 vector. So that is what is the difference. So, see the derivation of the element level governing equations is same, whatever we did for the two noded truss, same steps are here. Only thing is you are using different set of interpolation functions, the sizes of matrices are different, and now you have no different now instead of saying the axial forces, you are talking about shear force and bending moment in the internal force. Okay. So, this is the as far as the development of this element level governing equation is concerned. Now, we need to apply this to solve simple problems, let us say first. So, we need finally the form of the expressions for Ke. So, let us say that Ei is constant, although it can be variable, you have to account for in the integration. Let Ei is constant, Q is also constant. So, if these are constant, so then let us, how will you evaluate Ke? Ke is going to be integral 0 to L, Ei is constant, so I can take it out of the integration. Then your V is, as you see B is second derivatives, its transpose would be d2h1 by dx square, d2h2 by dx square and so on. So, d2h3 by dx square and d2h4 by dx square. So, this is B transpose, then B is d2h1 by dx square, d2h2 by dx square, d2h3 by dx square, d2h4 by dx square dx. So, this is B transpose and this is B transpose and this is B, this is what you get. When you multiply these, as you see, I am again giving bit more detail how you get to the final result. So, integral 0 to L, that integration is for each element after multiplication. Of course, the integration is after multiplication. It is not that you separately integrate this and this, this in the second matrix and then multiply them. So, first you will have to multiply and then integrate. So, typically the terms I will not write all of them. So, this is dx, this into this. So, first would become d2h1 by dx square into d2h1 by dx square. So, this is the first row and first column of this matrix. Then this into second will give you d2h1 by dx square, d2h2 by dx square and so on. Same way if you look at now the second row would be multiplication with this. So, which is d2h1 by dx square into d2h2 by dx square and then this into this, which is d2h2 by dx whole square and so on, so forth. So, this is the after multiplication. Now, you have to integrate all of these. So, you need the second derivative. So, you already know h1. So, let me look at how you get to this result. That is what little detail I wanted to give you. So, if you look at the expression for h1, now you need the second derivatives of all these functions. So, h1 we had written as, it would be there in your notes. So, it was 1 minus 3 x square by small l square and plus 2x cube by l cube. So, its second derivative, of course, you can, if you want to first write the first derivative, which is then going to be minus 6 x by l square and plus 6 x square by l cube. And then second derivative d2h1 by dx square is minus 6 by l square plus 12x by l cube. So, this is your second derivative of h1. Now, you see in case of linear truss, it was two noded truss element, it was constant. Of course, for the quadratic truss, it was linear function of x. Now, here because it is a second derivative, the same functions are cubic, but then second derivative is linear in x. And so, similarly, you can look at d2h2 by dx square would be similarly. So, if you differentiate 2 times the second shape function, you will get minus 4 by L and so this is plus 6x by this is 6x by L square and so on. So, you can write the derivatives of dh3 by dx square. If you look at the third shape function, its second derivative will be again 6 by L square, 6 by L square minus this is 12 x by L cube, and d2h4 by dx square will be, no, it's just I just wanted to show you how you get to final things. So minus this is 2 by L and plus 6x by L square. So these are the derivatives, and no, these derivatives you have to substitute here and then integrate each term. So you have to integrate this 0 to L, integrate this 0 to L, and so on. So when you do this integration, so finally you would find that Ke, when Ei is constant, I have the final result here, so I am writing that, you can verify. So Ei by L cube, this matrix comes out as, obviously it will be a 4 by 4 matrix. So this comes out as 12, this is 6L. Maybe when you compare with, so let me first write and then I'll tell you what I just wanted to say. And so this 6L of course is a symmetric matrix, 4L square minus 6L 2L square, and so let me only write the 1/2, so 12 minus 6L, and then this is 4L square, and it's symmetric, so now so you can write the other elements. These elements, they're symmetric, so you can write that. Symmetric meaning is, okay, let me I think write that, so this is minus 12, similar to this, and then this is similar to what we have here, which is minus 6L, and then this is similar to this, so this is 6L, here it is 2L square, then minus 6L. So this is your stiffness matrix. So you will again see that's a symmetric matrix, and of course you see that the diagonal elements are positive, but the off diagonal elements can be positive or negative. So both the combinations are there. Some of the off diagonal elements are positive, some of them are actually negative. So this is your element level stiffness matrix, which is 4 by 4 for Ei constant. If you look at the F external, which is again integration 0 to L and H transpose. So Q, since we said it's constant, so it's transpose into then dx, and H is no H1, H2, H3. So if you integrate each of those, integral 0 to L, and here what you have is no H1, H2, H3, H4, H transpose is this dx. If you integrate whatever expression you have got for H1, if you integrate it 0 to L, it will finally, you will find that that would actually turn out to be, now let me put this in under curly brackets, so that would be actually L by 2. Q I have written outside, so this would be L by 2. That is, this is simply, L by 2 is the integration H1 from 0 to L. Then if you do the integration of H2 from 0 to L, you will get that as L square by 12. You can check. So if you want integral 0 to L, let me do for H2. So as such, H2 is x minus 2 x square by L plus x cube by L square dx. And if you integrate this, so the integration terms are going to be, the first term is x square by 2, and you put the limit, so it would be L square by 2 minus the second term is 2 into L cube by 3L, and the last term is going to be L power 4 by 4L square. So when you simplify this, what do you get? You will get L square by 12. We can check. So multiply here. So this is 6 minus 8 and plus 3. So that is what you will get this. The if you do the integration of this will be L square by 12. Is it okay? So similarly, if you do the integration of H3, you will get again L by 2. If you do the integration of H4, you will actually get minus L square by 12. So this is what you get as your external load vector for constant Q when the transverse forces uniformly distributed across the element. Of course, for different elements it can still be different. So this is about the derivation of the stiffness matrix, the specific values of the elements of the stiffness matrix and the load vector. Now let's look at the application of this. So first simple problem, let us say we have a beam which is fixed, and now it is fixed at the two ends like this, and let us say that now it is subjected to a uniformly distributed load, although you can have any other kind of load, maybe half of it is loaded, half of it is not, and so on. So this is your Q, and let us say that no, the total length is 2L. I am just taking 2L just for the simplification. You can have any length, and then you can find out what is the small l, that is element length. So let us say that the total length is 2L, okay, that is small l is half of the total length. So this is the problem, and of course let us say that EI is also constant, and it is whatever is given is EI. So this is the problem we want to solve. So this is a beam under no loading in one plane, so it will obviously undergo bending in one plane, and that is what we have derived right now, the element level stiffness matrix. So now to solve this problem using finite element, we have to do the first discretization. Now discretization is, you will have to think of how many elements. So suppose if you think of only discretizing this into only one element, then what you will have is, see, because it is fixed at this end and it is fixed at this, at fixed ends you will have V and dV by dx both 0. So finally get, although no, we know the actual beam is going to deflect, but our one element solution will give everywhere 0 deflection and slope and also the strain and therefore stresses and everything. So we need to discretize this. So one element solution is a 0 solution basically. So minimum what you need to do is discretize this into 2 elements. So when you discretize say this into 2 elements, so let us say that means basically because each node is element is having 2 nodes, so the overall discretization will have 3 nodes. So let's say global node numbers are 1, 2 and 3, and the elements are, this is let us say element number 1 and this is element number 2. So this is now our discretization, that is 2 elements and 3 global nodes. So once we decide this, then is assembly. So in assembly what you are going to do, now since you have 2 elements, so assembly and each node having 2 degrees of freedom. So at the time of assembly we do not worry about what are the boundary conditions. So we first assume that how many nodes are there. So in this case 3 nodes, each node is having 2 degrees of freedom. So total degrees of freedom for the entire discretization would be 6. So taking that, we first assemble individual element contribution to the global system equations. So let me write it here. So it is going to be a bigger matrix. So you will have a stiffness matrix, say global stiffness matrix, and the degrees of freedom, global degrees of freedom, we are saying now the first global node is transverse displacement is V1, rotation theta 1, then second node V2, theta 2, V3 and theta 3, and then the right hand side you will have this external load vector plus internal load vector. So this is the structure of equations, and now because there are 6 global unknown, that is displacement as well as rotation. So this stiffness matrix is going to have 6 columns. So like global columns are 1, 2, 3, 4, 5 and 6. It is going to have basically 6 rows as well. So 1, 2, 3, 4, 5 and 6. Now when you look at the first element, now if you look at your the discretization here, the first element is consisting of global node 1 and 2. Its starting node is 1 and right end node is actually node number 2. So first node has got 2 degrees of freedom, V1 theta 1, second node has got 2 degrees of freedom, V2 theta 2. So the element stiffness matrix, which is of size 4 by 4, so locally you will have 4 rows and 4 columns. They will go to global first 4 columns here, 1, 2, 3, 4 and corresponding rows. So let me take, these are the rows and columns I have written. So for the first element, the contributions would go to the first 4 rows and columns. So let me take out here EI by L cube common, because I am assuming that both the elements are identical. So I can, and EI is same, element length is same, so EI by L cube, let us take it as common. So then the first row of the first element will go to the first 4 columns and first row. So those elements are 12, 6L and then minus 12 and 6L. That is the first row of stiffness matrix of first element. Then the second row will go to the second row of the global matrix, so which is this 6L 4L, you know it's there, I had written the stiffness matrix. So the same thing I am just putting it here, minus 6L 2L square. Then the third row will go to the third row here. So minus 12 minus 6L 12 minus 6L, and then you have fourth row will go to the fourth row of the global system. So 6L 2L square, and then you have minus 6L and 4L square. So this is the contribution of first element, goes into first 4 rows and columns based on the connectivity, the discretization, the way we have done the node numbering, that element connectivities. First element, first node is global node 1, second node is global node 2. Now when you look at the second element, the second element is, its first node is actually global node number 2 and second node is global node number 3, and corresponding to global node number 2, the degrees of freedom are V2 theta 2, which are in the global vector here are the third and fourth variable. So that means for the second element, the first row will go to third row, second row will go to the fourth, and third will go to the fifth, and fourth will go to the sixth row and column. So essentially the contribution of first element are going to be in third, fourth, fifth, sixth rows and columns of this stiffness matrix. So by looking at the connectivity and degrees of freedom at each node, you decide that which for a particular element, its individual element level contributions, where will they go to the global system. So in this case, because we are taking both the elements identical, that is EI is same, element length is same, so this term would be common as I have written it here. So the first row and first column of the second element will go to the third row and third column of this global system, and that is here 12. So I just add here, so we will have to do plus 12. Then the first row second column will go here, which is plus 6L, and then of course will continue minus 12 and then 6L here. Then the second row of second element will go to fourth row of the global system. So here again plus 6L and plus of course 4L square, and you have minus 6L and 2L square. And then the third will go to the fifth row, which is minus 12, then minus 6L 12 and minus 6L. Then you have fourth, which will go to the sixth row, which is 6L 2L square minus 6L and 4L square. So this is, you will see that there is a addition here. This third row, third column, third row, fourth column, fourth row, third column, and fourth row, fourth column. There is a addition from contribution. Second element, second node gets contribution from both the elements. That is what you see here. And whatever nothing is there means that is all actually 0. So this is 0, this is 0 here, 0, 0, 0, 0. So this is the assembled stiffness matrix. You call it as global stiffness matrix or system level stiffness matrix based on two element discretization of the beam. Then when you look at the right hand side, so right hand side you will have first element contribution to the external load vector, which is say QL by 2, then we have QL square by 12, and then we have again QL by 2 minus QL square by 12. That is the contribution of first element. Then second element contributions will go to third, fourth, fifth and sixth rows of this load vector. So here you will again have for the second element it is identical. So QL by 2, this is plus QL square by 12, and then again you have QL by 2 and minus QL square by 12. So this you get as your element level external load vector. So again there is an addition in the third row and fourth row. Then if you look at the external load vector, I think whatever I have written there, space is less. So let me just try getting more space here. So you have so the first element. Now let us put the superscript to differentiate between different elements. So we had for the first element shear force S1 1 and bending moment M1 1, and then the third and fourth terms are S2 1 and you have M2 1. These are the contributions from first element. Then the second element minus S1 2, that is shear force at the left end of second element, bending moment at the left end of the second element, and then shear force at the right end of the second element, bending moment at the right end of the second element. So again you see the contributions in the third and fourth rows are coming from both the elements. So superscript 1 means first element, superscript 2 here in the internal force terms is means element number 2. So this you get as your assembled system equation, call it as no global assembled system equation. This you call it a we had element level governing equation, this is global system equation. Global in the sense you are putting all the elements together, so that is what, and system means in this case the beam. Then we talk of boundary conditions. Now you can actually impose different kind of boundary conditions in this assembly. So but for the problem at hand, what are the boundary conditions we have now? We have to now prescribe the boundary condition in terms of basically your degrees of freedom and also your internal force terms, which are essentially your secondary variables. Degrees of freedom are primary variables, whereas whatever you have here, they are actually secondary variables. So what are the boundary conditions for this problem? So we have at this end it's fixed, meaning is it cannot move and also it cannot rotate. So we will have one is that V1 is equal to theta 1 is equal to 0. So these are two boundary conditions. Then the right end also, that is it is fixed at this end, and the corresponding degrees of freedom are V3 and theta 3. So we will have V3 equal to theta 3 equal to 0. So these are as far as the boundary conditions in terms of primary variable. Obviously the corresponding secondary variables would be non-zero. So this is an unknown, this is an unknown, this is an unknown, this is an unknown. So at the left and right you don't know what are these forces there, unless we solve for, when we solve we get the reaction forces. Now coming to this, so these we write by looking at the again the way we did earlier, the free body diagram of the the common nodes shared by both the elements in this case. So just take a section just left of this and just right of this. Again the way we did earlier, so this for the third boundary condition here I am considering the FBD of node 2, free body diagram of node 2. So if you do that, just for the purpose of representation, let me draw this as a finite sized basically space, but this actually just right and just left of this node. This is your node number 2. As far as the Q is concerned, because the length is 0, so the contribution of Q is actually 0, but there can be external forces in this. So the external force, let us say that there is a external force P, and there can be moment which are in the given problem they are actually 0, but if they are non-zero we will have to account for. So I want to first show a general case. So these are the external transverse force and external moment, externally applied moment. Then you have to show the reactions on the left and right. So those forces are let me write using different color. So this side you are going to have shear force. The outward normal to this section here is in the positive x direction. So the shear force you would show here. This is coming from the, now how will I show? S2, this is for the second element, S12 not S21. So this is the first node of second element and it is shown in the upward direction. So if you look at the element itself, second element, this side, here you would have shown this as actually this is the shear force on the left end of this element, which is first node and second element like this. The bending moment you would have shown as bending moment here at first node of the second element like this. So opposite of that, because this phase is common for this outward normal along negative x. So these are shown about and along negative coordinate direction. The opposite of that is shown here. So this is S12, and then you will also have moment. So moment on this face is, I don't know whether this color is not visible, okay. So you will have this moment which is M12. So this is what you are getting. Of course I have not completed, this side also you will have the term. So same way if you look at the first element this side, the right end of that again you will have a shear force which is at second node of first element like this, and bending moment which is second node of first element like this. Opposite of this will come here, the left face of the node. So you will have here shear force which is S21, and you will have a bending moment which is M21. Is this okay? The free body diagram of node 2. No, you have to, when you are drawing the free body diagram of node 2, you are just keeping the sign convention for the shear force and bending moment we have kept. So, it would automatically be consistent, because here no, this is a positive phase, and so I have shown the shear force along positive y direction, bending moment about positive z axis. This is a negative phase, this phase, because outward normal is along negative x direction. So, I have shown the shear force in the negative y direction, bending moment about negative z axis. And this will automatically be consistent, because these have to be equal and opposite. So, that would automatically come here and here, as you see in these two elements. And of course, you have to show for the complete free body diagram of the element, you have to show other forces here, similarly other forces there. Now, we write the equilibrium equations here. So, sum of the forces along y direction equal to 0 will give you, so you have no this S12 minus S21 and plus P equal to 0. So, you can say that S21 minus S12 would be equal to actually P. So, this is one equation. For the given problem, P is 0. So, that is S21 minus S12, what is written here, S21 minus S12 will actually be 0, since P is 0. So, for the given problem, this is equal to 0. If there is a concentrated force, then you, this difference you substitute as P. Same way, if you take moment of all these forces about z axis equal to 0, what will it give you? Is m12 minus say m21 and plus m. So, I am taking note this as positive here for the writing moment equation. So, m12 plus m, that external moment, and minus m21 equal to 0. And see, no, because it is a point. So, this section left and the right sections are just either left or right of that point. So, the distances of shear forces are 0 from the point from where we are taking moment. So, their contribution does not come in this. So, you can say that this m21 minus m2 will be equal to m, and for the given problem, because there is no concentrated external moment applied, so this will actually be equal to 0. So, these are the two more boundary conditions, that no S21 minus S12 equal to 0 and M21 minus M12 equal to 0. So, once we have done this, so now let us look at again this equation. So, we know that this is 0, this is 0, this is 0, this is 0. So, unknowns are V2, theta 2. The other side, if you look at this, now we know that it is 0, this is, we know that it is 0. Then these are unknowns. So, number of unknowns, if you count, this is 1, 2, 3, 4, 5 and 6. So, there are 6 unknowns and we have 6 equations. These are 6 equations. Again, the way we did earlier, first you can, the unknown displacements and the primary variables are third and fourth. So, first you can take out of these equations, third and fourth equations, solve for V2 and theta 2, and then do as a post processing, calculate the shear force S11, M11 and S22 and M22. So, that you can do later after calculation of V2 and theta 2. So, how do we calculate V2 and theta 2? So, first calculate V2 and theta 2. So, when you calculate V2 and theta 2, see, if you look at, basically you are taking the third equation. So, this 12 into 0 minus 6L into 0. So, that actually does not contribute. Similarly, the last two, this into phi3 which is 0, this into theta 3 which is 0. So, what you actually get is those two equations simply reduced to EI by L cube, which is common, and then you have here 12 plus 24 and these are 0, and that is 8L square. So, you have 24 0 0 8L square into V2 theta 2 is equal to, this side you get the contribution only from this load vector, which is again you see this is QL by 2 plus QL by 2, which is QL, and this goes to 0 because one is plus, other is minus. So, you get this as QL and 0. So, this is what you get as your equation. So, as you see, the solution here is, these are in this case it turns out to be a simpler set of equations for V2 and theta 2. So, you get basically you see theta 2 equal to 0, because second now right now the two equations are actually uncoupled. So, second equation directly gives you theta 2 equal to 0, first equation will give you V2 equal to Q L power 4 and divided by 24 EI. So this is your V2, theta 2 0, V2 is this, of course the V1 theta 1 and V3 theta 3 they are already given 0. Once you have done this, then you take the first equation and you can work out what are the values of the shear force bending moment. So just putting the values of V1 theta 1 they are already 0, V2 you got, theta 2 is 0. You put here in the first equation, you can actually calculate this. First equation is nothing but first row of the stiffness matrix multiplied by this is equal to this plus this. So you can calculate that way. So this is how you actually get the solution for the element, all the degree primary variables, and then you can do the calculation for the secondary variables. Then comes the your basically post processing. So if you want to do some calculation within the first element, you want to calculate the strain and then stress or displacement at any other point, you can do the post processing. So is this clear? So far are the things okay? Of course, in this case, as you see, the problem is symmetric. So the slope at center has to be 0, and that is what you get here. And you can check. Is anyone know what is the solution for this problem? Central deflection. Any idea? I don't remember. Although one can solve exactly what is the analytical solution for this case. Pardon? Yeah, divided. See this, small l is the element length. So actually this is capital L by 2 if capital L is the length of the element. Are you sure? What is the exact solution? Yes? Q let us say put capital L divided by 384 EI. This is for a fixed beam under uniformly distributed load. Are you sure? Yeah, this is for the fixed beam you have to. So say maybe we can check that. Of course, it can also be actually calculated. So if you look at here, this is small l is actually capital L by 2. So what you get is the 2 to the 4 to the 8 and 16. 16 into 24 is what? 384. So you see again that 2 element discretization actually gives you essentially the exact solution. And in this case also, if you look at the governing differential equation is 4th order with q constant. When you integrate it 4 times, your solution is going to have the highest order term of course would be actually having x to the power 4, whereas in the solution we are taking x cube. So it doesn't mean that the solution would be exact everywhere, but at the central node we get the deflection which is same as what we get as exact solution. So but in between you are going to get different results. So there is like similar to, if you remember, when I had done the discretization of a rod using 2 linear elements. So at the node points we had got the exact values of the primary variables, that is displacement there, but in between there was a difference. So same is the situation here. So now if you want to do post processing, so you want to calculate, let's say for element 1, these steps are actually exactly similar. So for element 1, V of x, that is V at any x within the first element, would be given by those same shape functions. What you have got h1, h2, h3, h4, and then the values of elemental degrees of freedom for the first element. So the left node having both V and theta 0, and then V2 you got this as q L power 4 upon 24 EI, and theta is 0, so this is what you get. So finally the displacement within the first element, as you see, is simply going to be h3, which is 3 x square by L square minus 2x cube by L cube into q L power 4 divided by 24 EI. So this is what you get, V as a function of x within the first element. So this is, of course you get this like a closed form expression, so I can use this expression to find out V at any x within the first element. Of course I cannot use this for beyond the first element. So this expression is only applicable within the first element. And if you want to calculate stresses, so then you need second derivative V, so that you already know d2V by dx square is obviously the derivatives of this, which is 6 by L square and minus 12 x by L cube into QL power 4 divided by 24 EI. Now you can calculate this this d2v by dx square at any location, or maybe just left end of the element capital X equal to 0, right end of the element is capital X is equal to small l, and in between maybe say capital X is equal to small l by 2 and so on. Once you calculate this, then the strain and finally the stress, so let me say sigma xx would be E times epsilon xx, and which is going to be E is nothing but minus y times this, so it would be minus y into 6 by L square minus 12x by L cube into QL power 4 upon 24 EI. So this comes as your stress. Of course, it will be also in terms of y, at y equal to 0, on the neutral axis stress is 0, at top and bottom it is going to be having maximum magnitude, and by putting the various values of capital X, you can calculate the stress. Of course, it is a linear function of x within the first element. So this is how you do these calculations, and similarly you can do for the second element. So for the second element, what you will do again? Yeah, any question? Yeah, so E will be there, obviously E has to be there, so this E will get cancelled. Yeah, thank you for correcting this. So this E will actually cancel out. This is E into epsilon. Not necessary. This is just for the convenience, so that I can easily write the assembled system equations. You can have EI. In fact, earlier we had done some problem where you have different properties. So you can have different EI in both the elements. You can have different L also. Say L1 and L2, and that you have to account for here in the assembly. So right now it's all LL. You can have for the second element, this could be simply L1. So where L and L1 can be different, L or L dash, whatever you want. So the element lengths, the properties of individual elements can be different. Element length can be different, the cross-sectional properties, they all can be different. So it's not necessary that, although as an example I have taken that. And even it can be a variable cross-sectional area, then you have to take care while doing the getting the stiffness matrix through integration. So during the integration, then you'll have to take care of variable EI as a function of x. So for the second element when you go, so V of x is going to be again those 4 shape functions. Now with this x being local coordinate of the second element, having origin at first node of the second element, again the shape functions remain same, h1, h2, h3, h4, and the degrees of freedom now if you look at for the second element, V is same, that is QL power V2, which is 24 EI, and then theta is 0, and then of course V3 and theta 3 they are 0. So this is what you get, right? So right now for the second element, because we have just used 2 elements, so except V2 there is theta 2, then V3 and theta 3 they are all 0. So this, as you see, it's actually theta 2, this is V3 and this is theta 3, but they are zeros. These are from the boundary condition, this came out from the solution. So again you see this is simply H1 into this quantity, and H1 is 1 minus 3x square y L square plus twice of x cube by L cube into QL power 4 divided by 24 EI. So this is, and same way then differentiating this, you can get the second derivative strain, and then stress you do the calculations. So this is how you use the beam element. Just this is a solution of a simple problem. Maybe suppose now rather than this boundary condition, suppose you wanted to solve a problem wherein you have a simply supported beam, let us say. So still load of course can be upward and downward. So if it is a downward load, put a Q as minus Q, rest of the things actually remain same. So if you have this and the boundary conditions are, let us say that it is having a pin joint here, maybe one side is roller. For the timing, let me keep it as statically determinate. So if you have this, of course this problem can be solved using minimum how many elements? Accuracy of the solution then is finally we need to take sufficient number of elements, but the minimum workable solution you can get here just with one element also, because the boundary conditions if you look at in terms of primary variables, so those are only V0 here, V0 here, so theta would still be non-zero. and then you can actually, using one element solution, you can calculate what is the deflection at the center. That may not be accurate, but you can get some solution. So you can try solving this problem using one element and using two elements. And when you are using two elements, then you will find that you will have to solve basically, of course, 4 equations, because no two rotations here will be unknowns, and the deflection and rotation here, those will be unknowns. You will have to solve for 4 equations. Sometimes you might have, so let me take another case. Let us say that I have a cantilever beam, there is one end that is fixed and subjected to still a similar kind of a load, let us say. Of course, you can talk of many different types of problem, but it is the end of the beam is resting on, let us say, on a flexible supports, it is elastic support. So let us say resting on a stiffness, spring which is having, let us say, stiffness capital, let us say K. And now if you want to solve this problem, still let us say using single element. So single element means I will have node 1 and node 2 here, and this is only one element, and of course let us say still know that EI is constant and this is Q, which is also constant, and I want you to solve this problem using one element. How will you do this? So one element means the element level governing equation itself becomes the global system equation. So EI by L cube, and this entire stiffness matrix here, you will have V1 theta 1, V2 theta 2, only 2 nodes. I am not writing the stiffness. The right hand side you will have load vector, which is QL by 2, QL square by 12, QL by 2 and minus QL square by 12. This is what we got. This side when you look at your internal forces, so see of course we will have minus M1, there is only one element, so I can, S first and then M. So you will have S11 and then you will have minus M11, then you will have S21 and M21. So this is what you will have. Now the boundary condition, one is that V1 is 0, theta 1 is 0, so left end, node 1, V1 theta 1 is 0. Right end, if you see, if you again draw the free body diagram of this node 2 basically, so you will find the node 2 free body diagram. Of course, right there is nothing, left you are taking just immediate, just left of 2 you are taking a cut section there. So see, we are taking the unknown, I am just going to conclude here. So here the unknown displacement is V2, and let us say that the undeformed configuration of this spring is when the beam is straight, the load is Q is 0, and then you apply the load. So the spring force for a positive V2 is still an unknown, and of course this problem is simpler, so we know that V2 is going to be in the upward direction, but in a general case you take as an unknown positive quantity. So V2 is a positive, the spring force is going to be here V2 into capital K. This is the force. There is no other force on the right, and this is the spring force. Is this clear? If V2 is the displacement, the spring force is going to be in the downward direction, and of course here you are going to have this shear force, which is basically S21, and you are going to have bending moment, which is M21. And now you write the equilibrium equation for this node, so you will get M21 actually equal to 0, and you will get S21 is equal to minus V2 into capital K. Is this clear? So when you take the write down the boundary conditions for this, so the boundary conditions are, number 1 is that V1 equal to theta 1 equal to 0, and second is at the right end M21 equal to 0, and you have S21 which is minus V2 into K. So this becomes the boundary condition, but this now you see this force is in terms of unknown displacement V2. So when you look at when you are solving problem, out of this you will take, because V1 theta 1 we already know them to be 0. So first we will take the second, third and fourth equation to find out V2 and theta 2. So if you look at second and fourth equations, EI by L cube, and the other two terms will be 0. So what they are multiplied with V1 and theta 1 which are 0. So you will get 12 minus 6L and 4L square this side, and the other side of course you will get QL by 2 minus QL square by 12, and plus here what you will have is minus V2K and 0. So now if you look at this, since this is in terms of unknown, so you take this to the left hand side, no, because this is V2 into K. This is here, no, you have to multiply this with the, no, I just forgot to write the degrees of freedom vector there. So you need to multiply here, what you have is V2 and theta 2 is equal to this. So what you will do, you will take this term when you write the first equation in this, whatever I have written here, which is now this Ei by L cube, of course 12 into V2 minus 6L into theta 2 is equal to QL by 2 minus V2K. That term you bring it to the left hand side. So actually it would be getting added with the V2 term here. So it would become like 12 plus, because Ei by L cube is common, so let me just rewrite that as KL cube upon Ei. So it will be just getting added here, this would be minus 6L, this remains here 4L square, and then you have V2 theta 2 is equal to, then this has gone now, so you have only QL by 2 minus QL square by 12. So this way you can handle if there are boundary conditions which are flexible boundary condition. In this case the right end is resting on a spring, so flexible support. You can have even a torsional spring there, and so that will give you a moment. You will get then in that case M21 as minus of stiffness of torsional spring into theta 2, and that you will be bringing, of course, in the second equation. So if there was some torsional spring, it would actually be getting added in this case at this particular location. So I think I want to stop here, and please complete all these problems whatever I have discussed. Maybe I will take some more problems on this and then we will proceed further. And please submit your assignment today to Mr. Babu. Those who have not submitted, those who have already submitted, you can just leave. If you have any doubts, questions, you can ask outside the class.